All right, folks, I'm John Frensley, and we're going to go over some fluids multiple choice questions. And I think we're going to do the free responses in a separate video. All right, I'm going to try and not take up a lot of your time. Student tears an electronic scale, sets a graduated cylinder on it, varying amounts of an unknown fluid added to the beaker, the total volume of the beaker, of the fluid and mass measured by the scale applied as shown. Okay, all good. What's the density of the fluid? The idea is that the students would simply take the slope of the graph. So if I take the slope, it looks like from 3 to 5, and it looks like we go over a 10,000th. So it'd be 5 minus 3 over 10 to the negative 3, which is 2,000 kilograms per meters cubed. All right, so let's keep going here. Student tears an electronic scale and then sets a graduated cylinder on it. Varying amounts of okay, so this is the same set leader here. That's what we call it. When the best fit line is drawn, a vertical intercept can be seen. The vertical intercept represents, well, they tear the scale first, and then they put the graduated cylinder on it. So the vertical intercept has to be an amount of mass. That's the vertical axis. It would have to be the mass of the graduated cylinder. All right, so that's just a test to see if your students can figure out what intercepts mean. All right, so this time, graduated cylinder is filled with water and set on an electronic scale. So it's set on an electronic scale after being filled with water. Student tears the scale after putting the graduated cylinder on it. Okay, and then adds identical, spheres of unknown metal to the cylinder. After adding each sphere, the mass measured by the scale and volume, the density of the metal. Okay, now this time, volume and mass are on the wrong axes. So if I take the slope, that will be the reciprocal of the density. So 1 over the density is volume over mass, because density is mass over volume, right? So that's going to be, let's choose 2 data points, maybe here and here. Okay, so that's going to be 4 minus 3 is 1 times 10 to the negative 4. And then that's over 0.6 minus 0.2. Well, I feel like reciprocating that. So to get the density, I'm going to take the reciprocal of what that is there. 0.6 minus 0.2, over 1e negative 4. That's a density of 4,000. All right, same set leader. When the student draws a best fit line, there's an intercept. That would be an amount of volume. Is it the, no, it's not the volume of the water and the glass the graduated cylinder is made of. It's just the volume of the water in the graduated cylinder. Sorry, I'm doing this video late at night after my kids go to bed. Okay, brass bar has a square cross-sectional length 1 centimeter. So let's see what that might look like. Okay, so it's 1 centimeter, 1 centimeter. Okay, the square side of the bar is placed on a student's hand. The pressure is 1 atmosphere. How tall is the rod? Okay, so here's the deal. I'm going to be using a few equations at the same time. And they're going to look like this. First of all, the force on the student's hand is the M times G of the rod. Pressure is force over area. So pressure is going to be mg divided by area. Now, what is M? M, mass, is density times volume, isn't it? Because density is mass over volume, so you get mass. So pressure is going to be mass, density times volume, mg, M is density times volume, over area. Now, what is volume over area? Well, if this is the area and this is the height, volume equals area times height. So then pressure is density times volume, area times height times gravity over area. So now we just get pressure equals rho GH. So that's actually the same as a fluid, pressure equals rho GH. So the pressure is 100,000 pascals. The density is 10,000 for the brass. G is 10. So if you divide, you just get a height of 1 meter. So you need 1 meter brass rod of any size will have the same density as water, as air. Isn't that crazy? Okay. Okay, so this is the same set leader. Another brass rod has a square cross-sectional length 3 centimeters. If this rod also exerts 1 atmosphere of pressure, then it is how many times as long as a small rod? We just said pressure is density, gravity, height. It's the same density. It's the same planet. It's the same pressure, 1 atmosphere, so it's going to be the same height or the same length. All right, so that's very interesting that you get that result from a solid. You think it describes a liquid, but it actually describes a solid. Okay, point P is in fresh water. What is the gauge pressure? So gauge pressure does not include atmosphere. So we're not going to have an atmosphere term, but we will have a density, gravity, and H for depth. The depth of this is 2 plus 5 plus 4. That's 11. So, well, isn't it just no? That's the whole point of this question. Students think that the ceiling matters. It really doesn't, because the pressure of the water can go around corners and things like that. Isn't that screwball? So 1,000 for a density, gravity is 10, and the height is 11. So it's 110,000 pascals. A vat contains water 4 meters deep. The bottom of the vat has an area 10 meters squared. How much force does the water exert on the bottom of the vat? So I'm going to use pressure equals, it's just the water, so not counting atmosphere. Density, gravity, depth. Density 100, gravity 1,000, gravity 10, depth is 4. So that would be 40,000 pascals. Now force equals pressure times area. The pressure is 40,000 pascals. The area is 10. That's 400,000 newtons. All right, same story, but a block of mass 100 kilograms is placed in the vat and floats. The pressure on the bottom of the vat increased by, okay, so here's the deal. You know pressure, force equals pressure times area, or you could say pressure equals force over area. But now what I'm going to do is I'm going to say the change in force is related to the change in pressure by these equations. What is the change in force? That's going to be the mg of the wooden block. So the wooden block floating in the water is going to add an additional 1,000, that's mass, 100 times G10, newtons, but that newtons will be distributed over the 10 meters squared of surface area, making 100 extra pascals, which is not very much. Yes, that's how fluids work. Newton's third law, if the buoyancy pushes up on the block to let it float, then the block pushes down on the water. All right, an extremely deep shaft is drilled into the Earth's crust. The probe measures the temperature, pressure and temperature, takes measurement. The temperature is found to be relatively constant. The pressure increases with depth. The data of pressure versus depth is shown in the graph. Scientists suspect that it draws the density of the air increases. Why is that? Well, this is pressure P, and this is depth H. So if I write pressure equals, let's say P atmosphere plus rho GH, then this is like the Y, this is like the X. So that means that this is the slope. The slope is rho times G, and this is the intercept, which we see right there, 100,000 pascals, 100,000 pascals. So that is the atmospheric pressure at the surface. And then the slope is density times gravity. So the slope of the pressure versus depth graph increases. That's why we can say that the pressure increases. In a water, which is not compressible, then it would look something like that. You know what I mean? Where it's a straight line, it's constant density. All right, that's a property of liquids. They have a constant density. Okay, 10 kilogram rock means 100 newtons because that's M times G. The spring scale reads 80, so if you have 100 newtons of M times G and you have 80 newtons of force spring, then the other 20 newtons has to be the force of buoyancy. Okay, same setup. What's the volume of the rock? I just said force buoyancy equals density gravity, density volume gravity. I didn't say that, but that's what it is. This is the volume underwater, which is all the volume because this is a sinking object. We just said the force buoyancy is 20 on the previous problem, equals density, 1,000, volume gravity is 10. So then I'm going to divide by 10 to get 2 equals 1,000 V. Divide by 1,000, I'm going to get 2 thousandths of a meter squared. Well, meters cubed, which is actually 2 liters. That's not a small ball. That's 2 liters is what that is. Let's see. Okay, 100 Newton ball. In this case, it says 80 newtons, which means that the force buoyancy would be 20 newtons. And the force buoyancy is density, the volume under the water, which is all of it, times gravity. Now here, only half of the volume is underwater. So that means you'll have half as much buoyancy force, but the thing would still weigh the same because its mass and weight haven't changed. So then the scale would read 90. That's a good question. I would make sure you work your students on that. Okay. The water is 1,000. The volume below the water is 8, and above the water is 2. What's the density of the raft? Okay, you can do this with a buoyancy and balance forces, which I will in a moment, but I'm just going to use my shortcut, which says that the volume under divided by the volume total is equal to the density of the object over the density of the water. This is a worthy thing to remember. So the volume under is 8 out of 10, the 10 total volume, and 8 of it is under. And then the density of the object over the density of water, well, then that would make it 800. Now, let's try something else. Let's say that the force of buoyancy, rho v under the water gravity, equals mg, the force of weight. So density of the water, the volume underwater times gravity equals mg. Okay, so then the g's cancel, and I'm going to say that the density of the water is 1,000. The volume under the water is 8. So the mass of this thing is 8,000 kilograms is the mass of this object. But then I'm going to do mass over volume to get density. And that's going to be 8,000 kilograms divided by the total volume, 10 meters cubed. So there's where you get your 800. All right. How many 50 kilogram students could stand on the raft before the raft is completely submerged? So what you could say is you could say that the force buoyancy, which is density, all of the volume now gravity, would equal the m of the raft plus the m of the students, g. All right, so all the volume will be underwater once all these students stand on the boat. I'm going to cancel that out. The density of the water is 1,000. All of the volume of the raft will be 10. We already know the mass of the raft from before was 8,000 kilograms plus the mass of the students, right? So 10,000, so the mass of the students is going to be 2,000. Each one is 50 times n. So then I believe that's going to be 40 students. Yeah, that's a lot of kids, isn't it? All right. Another way you could have done this is you could have said that the mass of the additional water displaced, mass of the additional water displaced is equal to the mass of the students. Okay, so what's the additional water displaced? It would be the density of water times the additional volume, which it would be the additional 2 meters. So 2 meters cubed. So when all these students stand on here, the final 2 meters cubed will actually go underwater. So you get 2 times the density of water, 1,000. That's where you can get to the mass of all the students together is 2,000. Okay, a helium balloon with a string attached is subject to 4 possible forces: weight, buoyancy, tension, and the force of air resistance. The child holds on to the balloon string so that the balloon is motionless shown. Which of the following correctly relates magnitude of the force of the balloon? Well, the motionless, so there's no drag, but there's a force tension, there's a force weight, and there's a force buoyancy, and they all balance. So let's say that buoyancy is equal to weight plus tension. Buoyancy is equal to weight plus tension. There it is. Now, the student lets go, and it will eventually reach a constant upward speed. The reason why is because there's still a force buoyancy and a force weight, but there's also a force of drag. Okay, the balloon would not go up except the force buoyancy is greater than the weight, but then the drag would make it stop going up faster, right? So here's a force of drag like so. An object with a volume of 100 centimeters cubed is placed in a cup. When the cup is floated in a pail of water, 200 centimeters cubed of water is displaced. What's the density of the object? Okay, so here's what I'm going to say. So I'm going to say that the mass of the object is equal to the mass of the water displaced. Really, they say mg equals mg. The weight of the object is equal to the weight of the water displaced. Or you could just say this, that the m of the object times g, weight, force down, force weight equals mg, is equal to the buoyancy force up, which is density of water, volume underwater, gravity. It's all the same thing. The g's cancel, and then this is the density of the object, volume of the object, equals the density of water, volume of the water. Okay, so density of the object, the volume is 100. The density of water is 1,000, and then this is 250. So let's get rid of that. 25 times 100 is 2,500. This one's tricky. No, it's the next one's tricky. So the object that's 1 meter tall, initially suspended for a rope, okay, and the object is lowered 1 meter per second of length, so that the object begins to enter the water and is completely submerged, and then we get this. So, what's the density of the object? What you're supposed to say is that this is when the object is out of the water entirely, and this is when the object is in the water entirely, right? So when the object is out of the water, you get mg, and you get force tension, and the force tension is 150, so the mg is 150 newtons, which means that the m is 15 kilograms. That's what you take from this. And then what you take from this is you say when it's in the water, the object it has a force tension of 50 newtons, and still an mg of 150 newtons, because, it's not going to lose its mass, which means that the buoyancy force is the remaining 100 newtons. Now, what is the force of buoyancy? The force of buoyancy is density of the volume under the water, which at this point is all of it, gravity. So that's going to be 100 equals 1,000 times v underwater times 10. So that's going to be volume under the water of 0.01 meters cubed. That's 10 liters, in case you're wondering. So now I'm going to take 15, or the density equals mass over volume. That's 15 over 0.01, and that's 1,500 grams per cubic. Okay, which of these was the object that went in there? Well, here's the story. The story is that the slope of the force versus height really graph. Like, think of it this way. Force of buoyancy equals the density times the volume under the water times gravity. Now, what is volume underwater? That would be like the cross-sectional area times the depth. Force buoyancy equals density, gravity. So then if I do buoyancy over x, I get the slope. The slope of this graph, it says time, but it might as well say height instead, would be density, area, gravity. So the key is that the slope depends on the cross-sectional area. So as this sphere goes under the water, its force versus time graph would first not be very steep because that's a very small area. Then it would be steep as the area is big, then not steep again as the area is again small. This graph, the area begins small, so the slope is not so much, but as the area gets bigger, the slope will increase. That's what these graphs would look like. This starts with a big area, so this would start with a steep slope, and then the area would be getting less and less, so the slope would be getting less and less. But this starts with the big area, steep slope, then a small area, then a big area again, so it's U. That's who this is. Steep slope for this big area submerging the water, then a small slope for this small area. I think you got the idea. All right, time for fluids in motion. A pipe with a circular cross-section carries water flows with speed v at all points. All right. The pipe splits into smaller pipes, all of which have circular cross-sections that are 1/4 the radius of the original pipe. Okay, so we're going to have smaller pipes, smaller pipes, smaller pipes, smaller pipe. You get the idea, okay? And it says that they have 1/4 the radius, which means they have 1/16 the area. If you don't know why that is, you need to see my video on geometric scaling. Okay, area times velocity equals area times velocity. It says the speed of the water at all points in the smaller pipes is also v. So the v is the same. So that means the area of the big pipe and the total area of all the smaller pipes is the same total area. Well, if each pipe has 1/16 the area, then there need to be 16 pipes in order to equal the same total area. Okay, if a pipe of radius r connects to a vertical column of water, a hole shoots water out. What is the speed of the water within the pipe? Okay, so the hole's radius is r. So the area, so I'm going to do the area of the pipe, velocity of the pipe equals area of the hole, velocity of the hole. Okay, the velocity of the hole is called v naught, and the radius of the hole is r, so it's going to be r squared. Isn't it pi r squared? Well, the pi is going to cancel out over here with the big R squared, and then that's the v in the pipe, which we want to know. So if I divide by big R squared, I get that. So it's just a continuity question. This is the same thing, but it's a Bernoulli question. What's it going to take to make this speed half as much? Okay, we're going to talk about the pipe, pressure pipe, plus rho g height of the water in the pipe. That's this h right here. Plus 1/2 density velocity in the pipe squared is going to equal the pressure at the hole plus rho g height of the hole plus 1/2 rho v at the hole squared. You can set the height equals 0 wherever you want. So I'm going to say the height equals 0 here. That eliminates this term. Both the hole and the pipe top is touching air. So they're both air pressure here, which cancels out. The speed of the water in the pipe is very, very slow compared to the speed that the water comes out. So I'm just going to let that go. For more on that, see my notes on Bernoulli, like why was I able to cancel out all those terms and call them 0. Density, gravity, this height right here equals 1/2 density velocity squared. So velocity equals the square root of 2gh, or you could say h equals v squared over 2g. Either way, if you make the height, if you want to make the speed half as much, you have to make the height 1/4 as much because of the squared or the square root, depending upon how you call it. All right, this one looks really complicated. Let's see what's going on here. Horizontal tube with a short, narrow portion has 2 identical vertical branches connect to it, both of which are immersed in a container of water. The left vertical branch is connected to the wide part, and the right vertical branch connected to the narrow part. Let y be the height of water A, and B, and y equals 0 is the height in the level container, where up is positive. Which the following correctly relates these heights when the air flows through at a constant flow rate. Okay, so here's the bottom line is this. So the pressure here, that was really supposed to be blue. The pressure here is all 1 atmosphere. 1 atmosphere. 1 atmosphere, because this air is not really moving. So it's at 1 atmosphere. This air is moving. Remember Bernoulli, faster air, lower pressure. So this is less than 1 atmosphere here, which means it's going to actually suck the water up some. But as the air goes into the narrow section, it goes faster, which means this is even less than 1 atmosphere than over here. So the water is going to go up even more. So YB is the highest, then A, then 0. They're both higher than 0. That's a good one. I would use that one. Ooh, what's going on here? Okay, a large container holds water. Its level is a height Y. Okay. Water is fed into the container by a height of pipe radius R, and the water leaves the container through a hole of radius R. Okay. Point 1 is in the center of the pipe, and point 2, center of the hole is the same height. And at the instant t equals 0 shown, water passes those points at the same speed. So these are at the same speed. If the flow speed past point 1 remains constant, how will the height y change? Okay, so here's what I'm thinking. I'm thinking that if the v is the same at the initial moment of these 2 points, at the initial moment, and this r is bigger than that r, then this is more flow rate in. Remember, flow rate is area times velocity. So with more area, that would be a greater velocity, a greater flow rate with the same velocity, and greater area, there's more flow in, less flow out. So what's going to happen is that the height is going to increase. The height's going to increase because more water's flowing in than flowing out. But here's the deal. You saw a second ago from Bernoulli, V equals square root of 2gh coming out the hole. As the height goes up, the velocity is going to go up, and then eventually the flow rate out is going to match the flow rate in because the velocity speeds up enough. So I think the height is going to increase at first, but then reach an asymptote or level off when the height gets high enough that this pees out fast enough for his flow rate out to match that flow rate in. Okay, let's see. A dam contains a deep lake, horizontal pipe. The lake water flows through the pipe at speed v1, flow rate phi1. When the pipe is replaced with another pipe, same height, but twice the diameter, the water flows through the new pipe, speed v2, flow rate v2. Which pair of equations correctly relate these 4 quantities? Okay, so twice the diameter is 4 times the area. Now, we showed with the Bernoulli equation before, we showed here that V is just radical 2gh. I would make the exact same argument to get to here. The pressures at the top and here are the same. The speed in the barrel is very slow. This could be height 0 or whatever. I'm going to make the same statement here. The speed in the lake is very slow. It's the same pressure on both sides. You get the idea. So then, if V is radical 2gh and the h is the same, then it's the same speed. It's the same speed. But flow rate is area times velocity. So if you have 4 times the area and the same velocity, you'll have 4 times the flow rate. So the new flow rate is 4 times the original flow rate. The new flow rate is 4 times the original flow rate. You have to teach your kids how to actually say this, or else they would say the old flow rate is 4 times as much as the new flow rate, and they don't know what they're doing because they're not saying it out like in English. Okay. A force on the plunger gives the water a gauge pressure of 32,000 pascals. What force is exerted on the plunger? Well, we know that because we know that force equals pressure times area. 32,000, pressure, and the area is 3 times 10 to the negative 4. So 3 times 32 is 96, and 10 to the negative 4 is going to 9.6 newtons. Okay, what's the speed of the fluid emerging? Well, pressure, this is going to be in the barrel. This is going to be in the needle. Pressure in the barrel plus rho g, height of the barrel plus 1/2 rho v squared in the barrel equals pressure at the needle plus rho g, height of the needle plus 1/2 rho v at the needle squared. Okay, now this point and that point are at the same height. Again, the barrel is very big compared to the needle, so that's super slow. If I work in gauge pressure, then the air pressure pushing on the needle is 0, and the pressure here is 32,000. Now, if you work in absolute pressure, you have 1 atmosphere here, but you also have 1 atmosphere plus the force over area, which makes the 32,000, and the 1 atmosphere would cancel out anyway. So I'm going to say the pressure applied equals 1/2 rho v squared. V is the square root of 2 pressures over density. That's the square root of 2 times 32,000 over 1,000. That's the square root of 64, which is 8.0 meters per second. Okay, the gauge pressure in the pipe is 2,000. So I'm going to say P for pipe and H for highest. I don't know. So the pressure in the pipe plus rho G height of the pipe, which is 0, plus 1/2 rho V squared pipe, which is 0 because the hole is so tiny compared to the barrel of the pipe, equals the pressure at this height, which is 1 atmosphere, which I'm going to count as 0 for gauge pressure, plus rho G height, which is what I really want to know, plus 1/2 rho V squared. But the V is 0 because the water molecules stop for a moment before going back down. And you get the pressure in the pipe, gauge pressure, equals rho GH. So 20,000 equals 1,010 H. Divide by 1,000, divide by 10, you get 2 meters. All right, and finally, the last multiple choice question. In each of the figures below, water flows through a horizontal tube past point X, then through a diagonal conduit, and then through another horizontal tube past point Y. Figures differ based on which points of the higher and larger diameter tube. Must the pressure at point X be greater than the pressure at point Y? So here's what I know about fluids. I know that the faster fluid exerts a lower pressure, and I also know that a higher point in the fluid is where there's going to be a lower pressure. So if the pressure at X is greater than the pressure at Y, then we need Y to be faster to make it have the lower pressure, and we need Y to be higher. Only B and D have Y higher. And Y is faster when it's narrower. That's continuity, so it's D. All right. I wonder if I was able to come in really short amount of time on these. Next video, we'll do the free responses.